In this video, we are going to discuss about ideal gas law. At the end of this lesson, students should be able to explain the qualitative of basic assumptions of the kinetic molecular theory of gases for an ideal gas. Students also need to define the gas law includes Boyle's law, Charles' law, and Avogadro's law. Students also need to sketch and interpret the graph of Boyle's law and Charles' law. And students also need to perform the calculation that involve gas law and ideal gas equation. Kinetic molecular theory. This theory states that the tiny particles in all forms of matter are in constant motion. This theory is commonly used to explain the behaviors of gases. There are four assumptions of kinetic molecular theory. The first assumption, a gas consists of tiny particles of negligible volume. Second, the intermolecular forces of attraction do not exist between gas particles. The third, the collision between gaseous particles are perfectly elastic. And the last one, the average kinetic energy of gas molecules is directly proportional to the absolute temperature. Gases consist of tiny particles. They are separated from one another at a great distance. As a result, there are a lot of empty spaces between gas particles. Since the size of gas particles is tiny compared to the distances that separate them and the volume of the container, thus the volume of gas is negligible. Gas particles are moved rapidly in random motion. They travel in a straight line and is not influenced by other gas particles. Thus, we can assume that there are no intermolecular forces between the particles of a gas. Gases consist of tiny particles of matter that are in constant motion. Gas particles are constantly colliding with each other and the walls of a container. These collisions are elastic. That is, there is no net loss of energy from the collision. The average kinetic energy of gas particles is dependent on the temperature of the gas. As temperature increases, the gas particles will move faster. Thus, the average kinetic energy also increases. There are four general laws that relate the four basic properties of gases. There are Boyle's law, Charles' law, Avogadro's law, and combined gas law. Boyle's law states that at a constant temperature, the volume of a fixed mass of an ideal gas is inversely proportional to its pressure. The mathematical expression of Boyle's law is shown below. Volume is inversely proportional to pressure. As K is a proportionality constant, thus PV equals to K. At a different pressure and volume, P1V1 equals to P2V2, whereas P1 is the initial pressure, V1 is the initial volume, P2 is the final pressure, and V2 is the final volume. The graph shows the pressure versus volume at a constant temperature. At a constant temperature, the pressure is inversely proportional to volume. When a graph is plotted of P versus 1 over V, a straight line is obtained. It shows that at a constant temperature, the pressure is directly proportional to 1 over V. If a graph of PV versus P is plotted, a straight constant line is obtained. This shows that at a constant temperature, pressure is directly proportional to P times V. Let's try some example. Question number 1. A sample of chlorine gas occupy a volume of 946 milliliter at a pressure of 726 millimercury. Calculate the pressure of the gas in millimercury if the volume is reduced to 154 milliliter at a constant temperature. As the initial pressure, initial volume, and final volume is given, calculate the final pressure of the gas. By using P1V1 equal to P2V2, P2 can be determined. Charles' law states that for a fixed amount of gas at a constant pressure, the gas volume is directly proportional to the absolute temperature. The mathematical expression of Charles' law is shown below. Volume is directly proportional to temperature. As K is a proportionality constant, thus V over T is equal to K. Keep in mind that the temperature is always in Kelvin. At a different volume and temperature, V1 over T1 is equals to V2 over T2, where V1 is the initial volume, T1 is the initial temperature, V2 is the final volume, and T2 is the final temperature. When a graph of volume versus temperature is plotted, a straight line is obtained. It means at a constant pressure, the volume is directly proportional to the temperature. Let's try an example questions. A sample of carbon monoxide gas occupies 3.20 liter at 125 degrees Celsius. Calculate the temperature at which the gas will occupy 1.54 liter if the pressure remains constant. Since the initial volume, final volume, and initial temperature is given, by using V1 over T1 equals to V2 over T2, the final temperature can be determined. Avogadro's law states that at constant pressure and temperature, the volume of a gas is directly proportional to the number of moles of the gas present. Avogadro's laws can be written in mathematical expression as shown below. Volume is directly proportional to the number of moles of gas. As K is the proportionality constant, thus V over N is equal to K. At a different volume and temperature, V1 over N1 equals to V2 over N2, where V1 is the initial volume, N1 is the initial number of moles, V2 is the final volume, and N2 is the final number of moles. If a graph is plotted V versus number of mole, a straight line is obtained. It shows that at a constant pressure and temperature, volume is directly proportional to the number of moles. Let's try an example questions. 2 moles of chlorine gas kept in a cylinder with piston occupies a volume of 49 liter. When another 3 moles of chlorine gas is pumped into the cylinder at constant temperature and pressure, the piston moves upward to accommodate the gas. Calculate the final volume of the gas. Since the initial volume, initial number of mole, and final number of mole of gas is given, we can use V1 over N1 equals to V2 over N2 to determine the final volume of gas. The volume occupied by 1 mole of any gas, or molar volume, depends on its temperature and pressure. At standard temperature and pressure, or STP, the pressure is equals to 1 atm, the temperature is equals to 0 degrees Celsius or 273.15 Kelvin, and the molar volume is equals to 22.4 decimeter cube. One mole of gas is equivalent to 6.02 exponent 23 molecules. At room temperature and pressure, or RTP, the value of pressure and temperature can be any given value, but the molar volume must be equals to 24 decimeter cube. 1 mole gas is always equals to 6.02 exponent 23 molecules. If carbon dioxide gas, nitrogen gas, and argon are filled respectively in the flask with same volume, thus we can assume that carbon dioxide gas, nitrogen gas, and argon has an equal volume. At a constant pressure and temperature, according to the Avogadro's laws, that volume is directly proportional to the number of mole of gas. Thus, we can assume that the number of mole of carbon dioxide gas must be equal to the number of mole of nitrogen gas and equals to the number of mole of argon gas. Take note that at STP, the pressure must be equals to 1 atm, the temperature that equals to 0 degrees Celsius, and the molar volume is 22.4 decimeter cube per mole. Now, let's try an example questions. What is the volume of hydrogen gas obtained from the reaction of 6.50 grams of zinc with an excess of dilute sulfuric acid at STP when pressure and temperature are constant? Writing the balanced chemical equation of the reaction, it shows that 1 mole of zinc reacted with 1 mole of sulfuric acid. It produced 1 mole of zinc sulfate and 1 mole of hydrogen gas. Using the mass given of zinc, we can determine the number of mole of zinc that reacted in the reaction. From the stoichiometric coefficient of the reaction, it shows that 1 mole of zinc produces 1 mole of hydrogen gas. Thus, if 0.10 mole of zinc that reacted in the reaction, it must produce 0.10 mole of hydrogen gas. At STP, 1 mole of gas will occupy 22.4 decimeter cube. If from the reaction 0.10 mole of hydrogen gas is released, thus it will occupy 2.24 decimeter cube. What is combined gas law? Combined gas law is a law that combines two gas laws, which includes Boyle's law and Chasles' law. The relationship between the pressure, volume, and absolute temperature are all present in the combined law. Boyle's law states that at a constant temperature and amount of gas, the volume is inversely proportional to the pressure, while Chasles' law states that at a constant pressure and amount of gas, volume is directly proportional to the temperature. The combination of Boyle's law and the Chasles' law, it can be shown as volume directly proportional to the temperature over pressure. By using the proportionality constant K, the equation can be written as PV over T equals to K. When temperature and pressure change at the same time, the pressure, volume, and temperature relationship for fixed mass of any gas may be expressed as a single equation. This equation is obtained from the combination of Boyle's law and the Charles law. In solving mathematical problems which involve two conditions, the equation is usually written as P1V1 over T1 equals to P2V2 over T2, with assumption that mass is constant, whereas P1 is initial pressure, V1 is the initial volume, T1 is the initial temperature, P2 is the final pressure, V2 is the final volume, and T2 is the final temperature. Let's try an example questions. A gas initially at 4 liter, 600 torr, and 66 degrees Celsius undergoes a change so that its final volume and temperature become 1.7 liter and 42 degrees Celsius. What is its final pressure? Assume that the number of moles remain unchanged. If initial volume, final volume, initial pressure, initial temperature, and final temperature are given, what is the final pressure of the gas? By using the formula of P1V1 over T1 equals to P2V2 over T2, by substituting all the value, we can determine the final pressure of the gas. The ideal gas law combines three gas laws: Boyle's law, Charles' law, and Avogadro's law. The ideal gas law equation describes how the volume of a gas is affected by changes in pressure, temperature, and the amount of gas. When Boyle's law, Charles' law, and Avogadro's law combines, it shows the relationship between temperature, pressure, and amount of gas to the volume. By substituting the R as a gas constant into the equation, it will derive an ideal gas law equation, which is PV equals to nRT. The ideal gas law can be used to determine the density, the relative molecular mass, temperature, and pressure of a gas. Take note that the gas which obeys the ideal gas equation is known as an ideal gas. For calculation purposes, pressure, volume, the gas constant, and the temperature must be in the correct unit. The value of R that suits the unit of pressure and the volume can be used as the following. Now, let's try an example questions. What is the pressure in 200 cm3 vessel if 12 grams of methane gas is heated to a temperature of 40 degrees Celsius? In the questions, the volume of the vessel, the temperature, and the mass of the methane is given. By using the mass given, we can determine the number of mole of the methane gas. By using the formula of ideal gas equation PV equals to nRT, substituting the value will give the value of the pressure. Density and molar mass of a gas can be calculated by rearranging the ideal gas equation. Since the number of mole of gas is equals to mass over molar mass, this formula can be substituted into the ideal gas equation. This equation also can be rearranged to relate with the density. Now, let's try an example questions. Calculate the density of ammonia in grams per liter at 0.989 atm at 55 degrees Celsius. Since in the questions are given the value of pressure, temperature, and the volume, by using this equation, we can determine the density of the gas. Now, let's try another example. A chemist has synthesized a greenish-yellow compound of chlorine and oxygen and finds that its density is 7.71 gram per liter at 36 degrees Celsius and 2.88 atm. Calculate the molar mass of the compound. Since the pressure, the temperature, and the density are given, by using this equation, we can determine the relative molecular mass of the gas. How to determine the relative molecular mass by using graphical method. From this equation, we can rearrange the equation in terms of pressure. To comply a linear graph equation, we can use y equals to mx plus c. When a graph of pressure versus density is plotted, we will obtain a straight line. We can determine the gradient of the line. The gradient is equals to RT over MR. Thus, we can determine the relative molecular mass. Now, let's take a look for an example of questions. Khalid and Ayman conducted an experiment to determine the relative molecular mass of gas X. The table below shows the experimental data obtained at 25 degrees Celsius. Determine the relative molecular mass of gas X by using graphical method. By using a linear graph equation, we can plot a linear graph of pressure versus density. A straight line will be obtained, and the gradient can be determined. By using the value of the gradient, we can determine the relative molecular mass. The concentration of a gas can be calculated by rearranging the ideal gas equation. Since the concentration of the gas is equals to the mole over volume, thus we can substitute the formula into the ideal gas equation.